It's time to move on to something else. Solutions. I make these songs up the second I press record, and I do not pre-plan, and you can tell. Solutions, meaning when stuff is dissolved in other stuff. You may actually remember way back in Unit 1, we talked about mixtures, and there were two kinds of mixtures. There were homogeneous and heterogeneous mixtures. Homogeneous is well mixed, meaning like it all looks the same. And a heterogeneous mixture was like you can look at it and you see stuff that looks different, like fruit salad. You can see different parts in there, or like concrete. You can see like tiny pebbles that are different from the other stuff, right? Homogeneous mixtures and solutions are the same thing. A solution is a homogeneous mixture where it's so perfectly well mixed that you can't see any different parts. Everything looks the exact same. So this unit is about water and solutions. But to understand solutions, we're going to have to understand water first. So let's talk about the tasty water molecule. It's got a Vesper shape of bent. That's back from Unit 6. Basically, the idea was that it's bent. It's like a straight line that you bent. And that actual shape ends up being important, that it's got this kind of like V shape to it, because that ends up being a big part of how water molecules interact with everything else in the universe, basically. Covalent bonds exist between the hydrogen and the oxygen. So they actually like share electrons. And it probably would have been more useful for me to do that with a different color. Here, there. This like overlap of the hydrogen and the oxygen is where they are sharing electrons in a covalent bond. Oxygen is more what we call electronegative, which means it's more greedy for electrons. It's sort of like a magnet, where all the electrons just sort of go like hang out over on the oxygen side, and that leaves you with like a positive side where the hydrogens are, because all the negative electrons are more attracted to that oxygen nucleus, so they just go like hang out over there. The oxygen's popular and the hydrogen is not. That means that water has an unbalanced charge. So the hydrogen is the positive side, and the oxygen is the negative side. It's not fully positive and negative. It's just sort of like a tendency. Think of it though like a magnet, where like a north and a south side of a magnet, you've got a positive side and a negative side of a water molecule. So what do we know about opposite charges in chemistry? We know that positives and negatives attract. They're very attracted to each other. This means that water is polar. There is a positive pole and a negative pole. Again, thinking about north and south poles on a magnet, it's the same idea, except instead of north and south, it turns out that we should be calling them positive and negative. But it's the same idea, your positive end and your negative end. Now, since the hydrogen and oxygen atoms in the molecule carry opposite partial charges, nearby water molecules are attracted to each other like tiny magnets. This attraction between the positive hydrogen and the negative oxygen from separate water molecules, we call it hydrogen bonding. So basically, what happens is, it's not like a real bond. They're not sharing electrons from one water molecule to a different molecule. Like the real bond is this right here, where hydrogens and oxygens are like sharing electrons and they have like an overlap. That's a real covalent bond. Hydrogen bonding is poorly named because it's not a real bond. It's more like hydrogen attraction, where like since this water molecule's oxygen is negative and its hydrogens are positive, And then like this water molecule has a negative oxygen as well. This positive hydrogen from one molecule and the negative oxygen from another molecule, those are attracted to each other. And that attraction is called a hydrogen bond, where they just sort of like hang out by each other. They're like Netflix and chilling. They don't like, they're not married. They're not going to stay together or like whatever. Not that you have to be married to stay together, but they're just hanging out. And that's going to be true for lots of hydrogens to other oxygens that are not part of the molecule they're attached to. So like this hydrogen right here will be attracted to this oxygen and they will have a hydrogen bond. And the same over on this side, where they're just positives and negatives doing what they do in nature, just attracting each other. So we can draw the positives and negatives next to each of these elements, where all these hydrogens are positive and all these oxygens are negative. And those negatives from one molecule and positives from another molecule are going to just attract like magnets. Like if you just throw a bunch of magnets together, they kind of sort themselves out to make the attraction work. So there's some vocabulary to go with this. Polarity is when a molecule has unbalanced charges from two poles, a positive and a negative pole. The positive pole on one molecule is going to attract the negative pole on another molecule, just like magnets. Water is polar because of this uneven sharing of electrons. Because one side is positive and the other side is negative, we call that polar. It's got poles. Negative and positive pole, just like north and south pole. Water molecules are attracted to each other by hydrogen bonding. It's not a real bond. They're not sharing the electrons. They're just hanging out. And compounds with no unbalanced charges are nonpolar. There's a vocab word for you. First time I mentioned it on the page here. So please notice when an ionic compound dissolves, the ions do something called dissociating. The positive and the negative separate. The water molecules will then surround the ions. So you can see like KF here, the potassium is positive and the fluorine is negative. And when you drop a KF, where I'll draw like here's a K, and here's an F, you drop it in the water and they split apart. And then the water molecules come in and surround them, where the negatives from the oxygens will get close to that positive K, potassium, and then the positive hydrogens are going to get close to that negative fluorine. So the positive ion is going to get surrounded by the negative oxygens from water, and the negative ion is going to get surrounded by the positive hydrogens from water. They all just sort of mob it, and then they orient themselves to the way they're attracted. And that'll happen anytime you put an ionic compound in water, if it dissolves. So let's mix it up a little bit. A solution is a homogeneous mixture, meaning that it is a well-mixed, uniformly distributed mixture. Everything's spread evenly. There's a bunch of types of solutions. You can have a liquid dissolving into a liquid. Like when you dissolve chocolate syrup into milk, you mix it up and then it all looks like all the same if you mix it up enough. You can dissolve a gas into a liquid. That's like carbon dioxide and soda. That's the bubbles. That's the carbonation. It's called carbonation because it comes from carbon dioxide. You can dissolve a solid into a liquid, like salt into water. So a liquid solution is usually the most common because you can easily-ish dissolve liquid or gas or solid into another liquid. Whereas it's you can't really like dissolve a solid into a gas. That's not a thing. Anything can dissolve into a liquid if they're compatible, which we'll talk about their compatibility in a second. Gas solutions, you can dissolve a gas into another gas. Air is actually a mixture of a whole bunch of gases dissolved with each other. Like oxygen is a gas dissolved in air, but it's actually, I don't know if you know this, it's only about 21% of air. And like 79% of air is nitrogen. And then there's like less than 1% of a whole bunch of other stuff like helium and carbon monoxide and carbon dioxide and methane and like whatever. But that's actually like a really closely balanced proportion. You may not know this. Your human body can only live inside like a really small range of oxygen percent. You would think that more oxygen would be like always better, but it's not. If it gets above something like 25-ish% oxygen, you'll actually die from oxygen poisoning. You need it to stay in this nice little range of 21% oxygen. It's something like 19 to 22-ish. Don't quote me on those exact numbers. I haven't looked them up in like a decade, but it's somewhere in there. You can like too little oxygen. It doesn't have to be 0% oxygen. It's like less than like 18% ish oxygen is enough that you suffocate. And then more than 23-ish, somewhere in there, you actually get oxygen poisoning from too much oxygen. Your body needs like a specific range to work. Whoops. Just locked my tablet screen by accident. So it woke up. Yes. Okay. Anyway, sorry. Whatever. Anyway, you can dissolve a gas in a gas. That's what air is. And we have to be really careful with our percentages of everything in air, or else lots of problems happen. And it's not just the huge problem of like carbon dioxide levels causing climate change. There's also just the simple matter of like, you get too much or too little oxygen there and every mammal dies. That's life. Solids can also dissolve into solids, like when you have an alloy. Brass is a mixture of copper and zinc. Steel is a mixture of iron and carbon. Now, typically the way they dissolve those is they do melt them down first, mix them together, but then when it cools off and it solidifies, they stay dissolved in each other. Like if you look at steel, you can't be like, oh, here's the iron section and here's the carbon section. That's not how alloys work. It's all perfectly well mixed and dissolved. Solutions are made up of two components. There's the solute, which is what there's usually less of, and then the solvent, which is what there's usually more of. The solute gets dissolved and the solvent does the dissolving. So the solute goes into the solvent and gets mixed in, and then when it's all mixed together, you have a solution where everything's all mixed together. And to the naked eye, it all looks evenly mixed and you can't tell the difference. So again, the solute goes into the solvent. If you ever forget which one, here's a nice little memory trick for you. The solute goes into the solvent, and you can think of the letter T in solute. Again, I should have changed colors before I drew that. You can think of the letter T in solute. Oh, no, don't do that, don't do that, don't do that. There, okay. Being like an arrow pointing you into the cup that is the V in solvent, kind of helping you remember which one goes into what. And there's usually less solute and more solvent. We call water the universal solvent. It doesn't literally dissolve everything in the universe, obviously, because if it did, then you couldn't like take a shower without dissolving. But it dissolves a lot of stuff. So we call water the universal solvent. Solutions where water is the solvent are called aqueous solutions, where something is dissolved in water. So we can identify what is the solute and what is the solvent. Like if I have 10 grams of sugar and 40 milliliters of water, the solute is the sugar dissolving into the solvent, which is the water. Or like 5 grams of salt into 50 milliliters of water. Again, the salt, NaCl, will be the solute. There's less of it going into much more water. If you have equal amounts of like alcohol and water, usually we're still going to say, hey, the solvent's going to be water, although they're kind of both at that point dissolving each other. Where this alcohol, though, is usually going to get poured into the water. Whatever's going into the water is the solvent. And then dissolving carbon dioxide into soda means that the solute will be the carbon dioxide and the solvent will be the soda, which guess what? The soda stuff is dissolved into water anyway, so it's still kind of water. This brings us to something called like dissolves like, which is this general idea that polar substances will dissolve in polar solvents, and this is also ionic substances will also dissolve in polar solvents. So basically anything with a plus and a minus will dissolve in something else with a plus and a minus. Water dissolves things that are polar and also things that are ionic. Where polar substances are, this is a biology word. Are you ready for this? They are hydrophilic. They love water, so they're going to dissolve in water. Polar stuff dissolves polar stuff. And non-polar substances are going to dissolve in non-polar solvents. So gasoline is non-polar. That means that tells us a couple things. One, it's not going to dissolve in water, which you kind of already know if you've ever gone in like a parking lot after it's rained and the puddles have like that rainbow get oil like floating on top. You know what I'm talking about? It separates and floats on top because they don't dissolve each other. And then the gasoline is less dense, so it like floats to the top. So they do not dissolve each other. Gasoline is non-polar and water's polar. They don't mix with each other. But gasoline would dissolve other non-polar things like mineral oil. Non-polar substances are hydrophobic. Again, it's a nice little biology word coming back to haunt you. Non-polar stuff dissolves non-polar stuff. So polar and non-polar together are not going to dissolve like oil floating on top of water. Oil is non-polar. It's going to float on top of polar water. It'll be less dense is why it floats on top, but they won't mix is the point. Non-polar stuff is hydrophobic. It won't mix with water because the polar pluses and minuses in the water molecules are not attracted to the non-polar oil because it doesn't have any pluses and minuses. This is also how like nail polish works, or nail polish remover, I should say. Nail polish is made of non-polar stuff, or excuse me, I said that backwards. There's some polar stuff in nail polish. There's not a lot of it because if there was a lot of it, it would just dissolve in water, but there is some. And then acetone, which is the main ingredient in nail polish, will dissolve the little bit of polar stuff, but part of an acetone molecule is also non-polar, so it'll dissolve the other non-polar stuff in nail polish as well. Like dissolves like. So nail polish is this interesting mixture of molecules that like one side's polar and the other is not. And acetone is similar to that, so they can dissolve each other. And that's how like nail polish remover works though, is you're dissolving the nail polish into the nail polish remover. Like you put the acetone nail polish remover on like a cotton ball or whatever, and then when you rub it on your nail polish, it dissolves the nail polish, and that's why the color is on the cotton ball when you take it off your fingers. This is also true for like certain types of permanent markers. If you have an oil-based marker, then you can actually dissolve the ink with like vegetable oil. So if you ever have lived in a house with small children, they just sort of have this knack for finding stuff they're not supposed to have, right? So if they have like a Sharpie they weren't supposed to get, and it happens to be one of the oil-based kind, and then they like color all over the floor or whatever, you could actually just dissolve that right up with some vegetable oil, because oils are nonpolar, and nonpolar will dissolve nonpolar because like dissolves like. Why soap is awesome is because soap has one polar end and one non-polar end. So soap can dissolve all kinds of stuff because the non-polar end will be attracted to all your non-polar oils and greases that you want to remove. So there's this like non-polar tail on soap molecules that is hydrophobic, and that will interact with all your greases and your oils and dirts that you're trying to get up that are also non-polar. But the polar end dissolves easily in water, so the soap will pick up all the oil and grease first, and then the water will dissolve with the other side of the soap molecule, this like polar head it's got that is hydrophilic. And then that will help us wash everything away. Yay, soap. Okay, last thing for this video, there are some ways you can make stuff dissolve faster in other stuff. We're gonna talk about when you dissolve solids into liquids and when you dissolve gases into liquids. So when you have a solid solute dissolving into liquid, there are 3 ways you could make it dissolve faster. First of all, you can agitate. That's a really fancy word that just means stir. If you stir it, it'll dissolve faster. You've probably noticed that before. You can also increase the temperature, meaning heat it. Like sugar dissolves a lot more easily in hot coffee or hot tea than it does in cold coffee or cold tea. And that's because when you heat it up, it dissolves faster. Basically, the hot like water in your coffee or tea, those molecules will move a lot faster, and that helps them to surround the stuff you're dissolving faster as well. So it just all goes faster. And then you can also increase the surface area, which really just basically means you like spread all the pieces out, which really just basically means you crush it. Crushing it. So like you take a sugar cube and it takes a longer time to dissolve because the water can't like get in there. But if you break it up into smaller pieces, then there's more like spots where the water can get inside and in between and start like surrounding and dissolving it. Because ultimately, remember, what dissolving is water molecules or solvent molecules surrounding all the molecules of the stuff that you're dissolving inside it. And then if a gas is getting dissolved into a liquid, there's 2 ways you can speed up doing that as well. One of those ways is to actually decrease the temperature, cooling it down. If you decrease the temperature, you can dissolve more gas inside of a liquid. So if you've ever been to like Atlanta, there's a Coca-Cola factory there / museum. It's like a real ripoff for tickets. It's like $25 for a ticket, and there's like not $25 worth of stuff to do in that museum unless you want to drink your weight in like Coca-Cola products from around the world, which there is a room at the end where you can do that, and then you like feel like you're gonna vomit for the rest of the day because you drank so much carbonated sugar. Anyway, that's not the point. The point is there is a room where they let you see the bottling process, and that room is actually kind of cold because they have this little injector that like goes into the bottle, and like you like hear the gas release, and they put the carbon dioxide into the bottle, the carbonation, and then it like moves down a conveyor belt, and they slap a lid on there. But the room is colder because the carbon dioxide dissolves better at a cold temperature. And the reason for that is because at a low temperature, the gas is moving slower. So it's able to like go into the soda and like stay there, versus at a higher temperature, we know that gases are like moving a lot more at higher temperatures. And that means that it's easier for them to escape if they're moving a lot faster. It's like, again, like the basic rule of toddlers. It's easier for my daughter to run away from me when she's in trouble if she's running fast, right? She can escape more easily. Same idea with gas molecules. The second way to make a gas dissolve more quickly is to increase pressure. And that is, again, because if they are under pressure, they're sort of getting pushed inside the liquid. Whereas like that's the reason why when you like open a soda, it makes that sound because you have released the pressure and now all the gas can escape. And that's why, like, if you're drinking from a bottle, when you unscrew the lid, the first like several times you open the bottle, it'll make some version of that noise. But every time you unscrew it, it makes the noise like less and less until at a certain point, the pressure has been released so much that a whole bunch of the gas has escaped and now your soda's flat. I actually like flat soda because I'm a massive weirdo. But when you like release the pressure, the gas can escape because it has somewhere to go. Whereas if you keep it under pressure, then it can stay dissolved and stuck inside of your soda. And that's also why in that room in the Coca-Cola factory, like they inject the gas and then the very next thing is it gets a lid slapped on it before too much of the gas that they just injected can escape. So there you go. That is solutions, part 1.